Hi everyone, welcome to our third and final lecture bite of the week for Astronomy 236. This time we'll be talking about light and the fingerprints of the elements. Now, you're all familiar with light. We use it every day. We see it. Without light, we would literally be in the dark. But what does it mean to light? What do physicists mean when we talk about light? In particular, when we think of light, we think of it as a form of energy that travels as a wave. And in particular, light travels as electromagnetic waves. You're also familiar with electricity, I'm sure. This is what powers our devices. And you're familiar with magnets, which we use to attach stuff to refrigerators. I'm showing two images here of people interacting with these forces. On the left, there's a woman touching a Van der Graaf generator. This generator is creating static electricity that's causing her hair to stand up. The electric forces caused by this generator are causing her hair to move. They're applying a force to it and they're causing it to stand up, even though normally it would fall down due to gravity. Magnets also apply forces. You can see here that this magnet is holding onto some paper clips. If I were to pick up that magnet, it would also go, the paper clips would go with it. When physicists think about electricity and magnetism, we think about how these objects, how these phenomena affect other objects, what forces they apply. On the left, I'm showing a visualization of the force caused by two plates that are charged by electric particles. So one of the plates is positively charged and one of the plates is negatively charged. Now, I've been telling you before how positively charged particles and negatively charged particles attract each other. Here, we're holding the plate stationary. But what it's causing is if we put another charged particle in the middle, it would definitely be attracted to either one or repulsed from one of the other plates. You can see that these lines here in the material this photograph is showing are showing the directions in which particles would travel if they were placed anywhere in this image. So if they were right between the two plates, it would go straight towards the plate. If it were further outside of the plates, it might curve around a little bit before it got there. There's a similar thing going on in this GIF of a magnet being bounced on a trampoline. These objects that it's bouncing into are iron filings. They're little magnetized pieces of material, and therefore they're attracted by the magnets. You can see that when they're bounced up and are freed from gravity for at least a little bit, they arrange themselves into these curling patterns. These patterns indicate how the magnetic field looks. These force fields, these electric fields and magnetic fields are really important for the production of light. So the next thing I want to emphasize is that electricity and magnetism, although they appear often to be discrete phenomena, are really intimately connected. So I'm showing two examples of how that works here. If what you do is if you put a battery, hook up a magnet nearby, and in particular, when they're using the magnets as contacts here, and connect a circuit so that you have electricity flowing from the positive terminal of the battery to the negative terminal of the battery, that produces motion. And you can produce these very simple electric motors with just a little bit of wire and a magnet and a battery. And another way that they're connected is that electricity can cause magnetic fields and vice versa. So this GIF here is showing an electromagnet. Those two clips, the red and black clips on the left-hand side of this GIF are connected to a battery. And this battery is then connected via those clips to a wire that's wound around a coil. This coil creates a magnetic field. And if you open and close the circuit and allow electricity to either flow when it's on or not flow when it's off, you can turn on and off this magnet. So this magnet can pick up these paper clips when the circuit is connected, but it loses them when the circuit is disconnected. So curling electric fields, curling around this core, create magnetic fields. And it turns out that the opposite is true as well. Curling magnetic fields wrapped around something can create electric fields. And this interplay of curling electric fields and curling magnetic fields is what allows light to propagate. It turns out that if you start off one of these changing electric fields, it will create a magnetic field, and that magnetic field will then recreate that electric field. And these two fields will oscillate around each other for very long periods of time throughout, parsecs, light years in space, and create these waves. And these waves are light. Light travels via these waves. So now that I've shown a little bit about how electric fields and magnetic fields can cause waves that travel as light, I want to go a little bit into how do we learn about the properties of waves and what are some of the things that we care about. So one of the main properties of a wave is its speed. So how quickly does the wave move through whatever medium it's in? So in the case of electromagnetic waves or light, how quickly do these electric and magnetic fields travel through space? In the case of this GIF here, how quickly do these waves travel through water? And the way you measure this is pretty simple. You just ask how fast is that peak or is that trough moving along? You calculate the amount of distance that that peak has gone, you divide it by the amount of time to get a speed in miles per hour or meters per second, as a physicist would typically measure. Typically, the speed of a wave depends on what it's traveling in. The typical speed of waves in water are about 5 to 20 miles per hour, so they don't really go that much faster than humans can move around. And you've probably experienced that by trying to outrun waves in pools or on the ocean and the beach. On the other hand, light waves, the speed of light is much, much faster. So the speed of light is about 670 million miles per hour. Another property of a wave that's really important is the wavelength. This is just the distance between two consecutive peaks or two consecutive troughs on this wave. This will come in handy later on when we talk about the colors of light. Related to the wavelength is the frequency of the wave. This is a little bit more difficult to measure just by looking at it. You have to time it. So the frequency of wave is how many peaks of that wave pass through a point at any given amount of time. So in this image, I'm using the animated version of this wave in water, and I've added a pink line. So I want you to watch this pink line and count how many waves travel through it as I start this timer over here on the left. So I'm going to start the timer right when this crest hits. So now the timer is going. I'll let it run for 10 seconds. And I want you to count how many peaks make it through that wave. So there's 10 seconds. I counted 4 peaks. So the frequency of this wave is about 4 cycles every 10 seconds. Or if you just do that division, about 0.4 cycles per second. These 3 properties of waves are related by this simple equation. The frequency of the wave is equal to the speed divided by the wavelength. What this also implies is that if you have a speed that is constant, like in the case of light always travels at the speed of light, then the frequency and the wavelength are inversely related. The higher the frequency of the wave, the lower its wavelength must be, and vice versa. And finally, an important property of a wave is how much energy it carries. So if you've ever been in the ocean and have been playing in the waves, you know that they can pack a punch, they can knock you over. So they're carrying energy and have the ability to do work and exert forces on people. So how much energy is that? The thing I want you to take away here is that it depends what the wave is traveling in, whether it's in water or in string or in light. But the general rule is that the higher the frequency, the faster these waves are traveling through a single point, the more energy is carried. So now let's go back to light. We have talked about how light is a wave, and we've talked about how waves can have different wavelengths and different frequencies. It turns out that the different wavelengths of light correspond to different colors. Our eyes are actually able to determine the wavelength of a given particle of light or a given wave of light. So if you spread out the light that you see from something like the sun with a prism, you can spread out these colors and shoot light with different wavelengths into different positions on this piece of paper. So you see the rainbow, the Roy G. Biv pattern, red, orange, yellow come first over on the left-hand side, and then it goes into green, blue, indigo, and violet on the right-hand side. So that's a sequence from long wavelengths. Red is a long wavelength to short wavelengths. Violet is a short wavelength. But you might then wonder, what about on the edges of the red side and of the violet side? Is there any light that's either bluer or redder than what we can see here that we're just not seeing? And it turns out the answer is yes. The light that we can see with our eyes is only a tiny fraction of all of the possible wavelengths of light that can be produced. So in this diagram here, I'm showing the different wavelengths of light. And in the middle of the diagram is the visible wavelengths. These are the familiar colors of the rainbow that we see with our eyes every day. If you try to observe light that has longer wavelengths than red light in the visible, you get into the infrared light. This infrared light is something that we study in astronomy frequently. If you go further and further, you get into microwave light. And yes, these are the microwaves that you use to warm up your food. So microwave light can be used that can be produced with our microwaves, and we use it all the time. And then even further to longer wavelengths, you get radio light. And yes, radio light are the radio signals that we use to communicate and beam songs from powerful antennas into our cars. Going the other direction, if we ask the question, is there any light that is shorter wavelength or higher frequency than the blue and indigo and violet light that we see with our eyes? The answer is also yes. First, we get the ultraviolet light. This light is a little bit shorter in wavelength than the light that we see in the visible. And it's particularly something that we care about when we go out into the sun, because ultraviolet light is the stuff that gives us sunburns. Going further to shorter wavelengths, we get into the X-ray light. The X-rays are the same X-rays that you get when you go to the doctor. This light is so short wavelength that it can go right through the material in our bodies, but it gets stopped when it goes through the denser material in our bones. And that's how we can produce images with X-rays. And the very shortest wavelength light that we think about in general are gamma rays. And these gamma rays are so short wavelength and so high energy that we don't really use them in our everyday life. It's possible that they're even shorter, and there definitely are even shorter wavelengths of light than gamma rays, and even longer wavelengths of light than the radio. But we don't typically work with them in human scale, just because then their wavelengths would be either so short or so long they're difficult to produce and difficult to use. I alluded to this earlier, but I talked about how the frequency of light is related to the energy that it carries, or the frequency of any wave is related to the energy that it carries. Waves that have high frequency carry more energy, and therefore waves with shorter wavelength of light carry more energy. So this is why when we worry about the damaging exposure to light, we focus mostly on ultraviolet light and X-ray light, because these are the light wavelengths that have the highest energy and therefore the highest ability to potentially harm us. So here I'm showing a sunscreen which proudly advertises that it blocks both UVA and UVB light. UVA and UVB are just different subcategories of ultraviolet light. And I'm showing here a fellow who's wearing a lead vest to protect himself from X-rays. Perhaps he works as an X-ray operator or a doctor who works with X-rays quite a bit, and he wants to make sure that the X-rays don't get into his body and release their energy in his cells and cause damage that way. So I want you to recall from our last lecture bite in our quantum mechanics lecture that particles in quantum mechanics that are trapped have discrete possible energies. And to remind you of how we got to this, I'm showing you this image or this video of a student who's vibrating a string and causing a standing wave pattern. And this stationary standing wave is one of a discrete set. You can have these waves with one lobe or two lobes, in this case, 3 lobes that move up and down, but they don't go anywhere else. So these particles, which are described by wave functions, which behave like these waves in string, have discrete possible energies as a result of this. One way to trap a particle is to put it in an atom. So in particular, when you have a proton and an electron that bond together to form a hydrogen atom, they're attracted to each other because of the electric charge. This poor cat is also being attracted by these styrofoam peanuts in the same way that a proton and an electron are attracted to each other. So this electron is essentially trapped close to the proton, and it's confined to a certain region around it if it doesn't have enough energy to escape. So therefore, this electron, because it's a quantum particle, must have discrete possible energies the same way the waves in that string have discrete possible frequencies. So I also want to remind you of wave functions and how they look like heat maps in soccer. The brighter areas in this image show you where the particle is most likely to land, and the greener areas show you where it's unlikely to be. So this will help you interpret this next figure here. So this figure here shows solutions to the Schrödinger equation of what happens to an electron when it is trapped close to a proton. It has, as I just mentioned, discrete energy levels. So these energy levels are shown on the vertical axis of this diagram. So the one labeled n=1 is the very lowest energy level that this electron could possibly be in. If the electron gains a little bit of energy, it can jump up into energy level number 2, which has a couple of possible shapes and orientations. And if it goes higher and higher in energy, it can be in these other possible configurations around the atom, or around the proton. But the key here is that it only is allowed to stay in these discrete energy levels. It can't go in between them. It can't have a half energy level. So if you imagine that you have an electron orbiting this proton that starts off in the energy level, the third energy level, n=3, and it falls down to the n=2 energy level, what's the result of this? So recall that energy is conserved. We can't create energy, we can't destroy it. It just has to go somewhere else. The way the energy from this electron's fall is released is as light. So the energy releases an electromagnetic wave that carries some light away from this system. Because it's a relatively short duration event, the rise and fall of that electron happens very quickly. It only produces a very short burst of light. We call such a burst of light a photon. It's a little packet of waves that travel along through space. Photons are the fundamental particles of light, or the fundamental quanta of light, in kind of the same way that electrons are the fundamental quanta of electric charge. They have one electric charge between them, and light beams and photons have one unit of light. So here's the key point. Because these energy levels in the hydrogen atom are always the same, and they're set by the Schrödinger equation, and because the difference in energy between the n=3 level and the n=2 level is also always the same. The amount of energy that's released as light is always the same. We know that this energy goes away. We know that it goes away in the form of light. So what this means is that electrons and hydrogen atoms can only create light with certain specific energies. And because energy in light corresponds to frequency, which corresponds to wavelength, which corresponds to the color of a particular particle of light, hydrogen only produces a very specific handful of colors of light. These are very sharp colors. They're not similar to any other nearby colors produced by hydrogen, and they look kind of like this. So this is what hydrogen looks like when it's glowing in gas form. So this is kind of like a fluorescent light bulb. The hydrogen gas is put inside of a tube, and electricity is passed through it, which provides energy to the atoms in the hydrogen and causes the electrons to rise up to a higher energy level. And then they fall down and they release light, and we can see that light with our eyes. If we take these hydrogen lamps and we take the light they produce and we shine it through a prism or through a grating, which is kind of like what the back of a CD looks like when it reflects a rainbow. So if you take your CD and you shine it to the sun and then you reflect that light, you can see a rainbow pattern caused by that. So what we do is we use these prisms and CD gratings to spread out the light and see the different colors. This we call a spectrum. This is what it looks like when you do this to hydrogen. You get these 4 main bands of light. So there's a really bright red band, there's a really bright blue band, and then there's 2 slightly less bright purple and even darker purple bands. This is the spectral fingerprint of hydrogen. These lines are unique to hydrogen, and this pattern is unique to hydrogen, and it's universal. Every hydrogen atom produces a pattern like this. The red line over on the right is caused by the hydrogen electron falling from the n=3 level to the n=2 level. The blue one is from n=4 to n=2, and the purple one is from n=5 and n=6 to n=2. So this is another thing you can see. The larger the difference in energy, the higher it starts off and the lower it falls, the higher energy the light ends up being emitted, because purple light is shorter wavelength and therefore higher frequency and higher energy than red light. So this is hydrogen's spectral fingerprint. Here's another way of looking at this. So often in astronomy, we plot the brightness of something at different wavelengths in a plot called a spectrum. So here's what it looks like. The y-axis is showing you how bright the light is, and the x-axis is showing you the wavelength of that light, or the color. So over here on the right, around 650, you can see the red line, which was the n=3 transition to the n=2 transition. A little bit to the blue, you have around 480 nanometers, the n=4 to n=2 transition, and they show up as these spikes in the spectrum. So hydrogen has its own fingerprint, but all of the other elements have their own uniquely identifiable fingerprints too. I'm showing here the hydrogen spectrum on the left, which we just looked at. And in the middle, here's the neon spectrum. You can see that neon is a lot more complex than hydrogen, has a lot more lines that can show up. This is because neon has more electrons, which are therefore more able to produce different patterns. On the right, there's a similar spectrum, but for mercury. Mercury also has a different pattern than these other 2. And the way we assign these fingerprints is we can either measure them in the lab using lamps just like these and measuring where the colors of light are emitted. Or in simple cases, we can calculate them directly from the Schrodinger equation. It's possible to take the Schrodinger equation, solve it, and measure and read off from that equation what the frequencies and wavelengths of hydrogen transitions are, and produce this spectrum here completely from math. So for some historical perspective on this, I've included another clip from the Fabric of the Cosmos video.
So how did we discover them? These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun, how a ball arcs through the sky, how ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense, until about 100 years ago, when scientists were struggling to explain some unusual properties of light. In particular, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smeared, kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
All right, now that we've finished watching this clip, the last thing I want to talk about is a caveat. So I've been talking about how elements have these sharp lines that produce spectral fingerprints. But this isn't always how light is emitted. In some cases, and in particular denser materials than gases, the lines they produce are smeared out. So here I'm showing light that's being produced from an electric stove. And you can see that these burners are all on and they're all glowing hot. So what does this glowing hot light look like? It's called blackbody radiation. So glowing light produced by objects, every object, has a characteristic spectrum, and it's fairly smooth. You can notice that there are no sharp lines like there were in the spectrum of hydrogen and neon and mercury lamps. And in particular, hotter objects produce both more light. So this red curve here is the hottest object they're showing, and it produces a much higher total amount of light on this graph. This is also a spectrum shown the same way as that other plot was earlier. The cooler object, the 3000 Kelvin object, produces less light overall than the hotter objects. The other thing to notice is that the hotter the object, the bluer the light it produces. It's a little bit hard to see this if you're comparing the 6000 Kelvin curve to the 5000 Kelvin curve. But if you compare where the peak of that 6000 Kelvin curve is to the peak of the 3000 Kelvin curve, it's moved quite far over. And the 3000 Kelvin curve peaks over in the infrared, while the 6000 Kelvin curve peaks in visible light. And I think I'll stop there.